Welcome to this seminar over the summer. So today we are very happy to have Professor Howard Lee from UC Irvine visiting us and then tell us his exciting research in metal optics. So I have to pull out this piece of paper to read his distinguished achievement. So Professor Howard Lee currently is an associate professor in the Department of Physics and Astronomy in UC Irvine. It happened my boss, my PhD supervisor, is also in the same department. So yesterday I looked through the list and then discover Professor Wilson Hall is also there. Okay. Yeah. Yeah. So before joining UCL, Professor Lee was with physics department at Baylor University and also Texas A&M, and even before that, he was a postdoc in Caltech, working with the very famous Professor Harry Atwater, right? And then so going further back, he was actually educated in Germany and got a PhD there in 2012. All right, but still, if you want to trace back, Professor Lee actually is local. Yeah. He's a graduate of CTU, and then you were in applied physics. Applied physics. So you can see, locals actually can be, truly distinguished. So he published many good papers, including papers in Science, Nanoletter, and Advanced Material. And he also received many awards, including some recent award, such as UCI Dior Innovation Award in Physical Science, ICANN-X Young Scientist Award in 2021. And so on. So that's a long list. So pardon me for not reading all of them. All right. Otherwise, they would kill me because I spent too much time reading all these things. Okay. So today, Professor Lee will tell us his latest research in active zero index and net photonics. So let's welcome Professor Lee.
Okay, thank you for the introduction. So I'm Howard Lee from UC Irvine. So from the physics department at the same time from the Beckman Laser Institute as well. So I'm also ambassador for the Optical Society as well. So we're trying to engage students and also connecting students to the Optical Society, or even helping them to develop professional developments, or even connecting with different scientists and staff and so on. So first of all, really thank you for the opportunity to be here to tell you something about my research. It's great to come back to Hong Kong. I haven't been back to Hong Kong for a couple of years, and I think it's the second or third time here for me, BUHK. So it's really great to be here to tell you about my research related to this kind of metal optics, and also connecting with some nanophotonics optical fiber as well. But before I go into detail of my talk, probably I just quickly introduce a little bit more about myself. So I origin from Hong Kong, as Professor So already mentioned. I spent most of my time in Hong Kong and City University of Hong Kong. But in my last year of my undergrad, I have a chance to move to Sydney as an exchange student. So I have a chance to work in the group called Kudos and with the Ben Andertons. At that time, it's quite good research institute in Australia. And this year in Sydney actually changed my life quite a lot, because it's the first time I do research in photonics. That's why I sort of having the passions and motivation to spend my whole career in optics and photonics, definitely important for my life. But at the same time, it's also I met my wife there as well, so definitely important for my life as well. So that's why I always encourage students, graduate students, undergrad students, if you have a chance, go overseas to explore. You can see different culture, different environment. You may find your future career, but at the same time, maybe find your future spouse as well. So it's good to explore overseas if you have a chance. But anyway, after that, I moved to Germany in Max Planck Institute for the science of light as a PhD student, working with Philip Russell on photonic crystal fiber. And then I moved to Caltech in the US in Harry Atwater Group working on nanophotonic metamaterial. And then I start my group in Texas in Baylor University, like as an assistant professor. I worked there around 5 years. But after that, I find I like California more. That's why I moved back to California, UCF, 2.5 years ago as an associate professor. So my research group basically focusing on nano optics. So looking on light matter interaction in small dimensions. We have a couple of different areas working on. Just quickly tell you, for example, we're working on this kind of matter surface, kind of nanophotonic structure, integrating to fiber optics, and then studying some new material called seal index material. I will tell you more about this in this talk, and then try to combine with different device imaging capability at the same time, making maybe circuit or device. So we're looking for fundamental physics and optics, but at the same time looking for different application on imaging, sensing, or even medical application, because in the US, typically you may need to have some application in order getting funding as well. So it's a little bit hard to be a pure science, but anyway, we kind of looking on the physics optic, but at the same time looking for different application as well. So if those of you haven't been Irvine, California, this is the kind of a campus map here. You can see we are in the physics department, but our lab also in the Applied Innovation Building, sort of hoping to apply some of the research to making innovations or device or commercializations. At the same time, we're working together with Beckman Institute on some of the medical application as well. So Irvine is a really nice city. They have a lot of Asian community and also a lot of company nearby. A lot of Asian food as well. Certainly it's not as good as Hong Kong, but it's one of the best in the US, certainly. And also we have a couple of beach, really nice beach nearby. So I have a 7-year-old son, so we're always enjoying the beach times over there as well. So we always looking for, let's say, visiting or collaborations, at the same time looking for students and postdocs from time to time. So if you are interested, let's say, interested in the bridge or California or our research, feel free to reach out at the same time. Happy to extend any collaboration as well. So so certainly, let me tell you more about what is nano optic first, so as some of you may not be too familiar about nano optics. So as you may know, when the light interact with the mediums, let's say a prism here, you have a lot of fundamental optical property you will find. And many of them, you actually learn it in your textbook or in your during your high school. For example, you learn about reflection, transmission, and so on. Many fundamental optical property you already know really well. And we study this optical phenomenon for a long time. For example, some of the property, let's say the Sells law, reflections already studied or understood more than 500 years ago. So it seems like we understood really well all the optical phenomena and property. It seems that nothing new we can study. But this is exactly what we try to do in nano optics. We want to find something anomalous. For example, abnormal reflection, and so on, which is completely different than what you learn in the textbook. And this is exactly what we try to do in nano optics. And this has been inspired by actually one of my favorite scientists, Richard Feynman. He gave a really important lecture like at Caltech around 50 years ago. He mentioned that there are plenty of room at the bottom. That means when you're going down to a really small dimensions, let's say atomic scale or nanoscale, all the property will be really different. For example, material property, electronic property, or even optical property will be really different than a bulk material. And this is exactly what we try to do. We want to study the optics in a really small scale. We're talking about the nanometer scales. So we can do that because we can actually fabricating structure, really small structure really well nowadays, because we have a really good nanofabrication technology. We can making structure maybe smaller than waving of light, or even let's say 10 nanometer, 20 nanometer, really small dimensions. At the same time, we have a lot of new material we can study. For example, let's say some so-called plasmonic material, two-dimensional material, or topological material. A lot of different material we can, new material we can study nowadays. So that's exactly what we try to do. We want to looking for new material, new structure, and studying physics and optics in the nanoscale at the same time apply for different applications. So this is some of the goal of our research here. But certainly there are many different topics in nano optics. I will try to just highlight a couple of important concepts here. one important concept is called this kind of matter surface here. So you can imagine thinking this is like an ultra thin optics. So this is actually one of matter surface structure you can see. We basically have many different scatter and resonator. We're looking on the top view here. And this kind of matter surface have been discovered like around 10 years ago by the group, Capasso group in Harvard. So what they find is that when you have this kind of nanostructure matter surface, when you shine light on top, instead of a normal reflection or normal reflection you typically see, you can have some anomalous reflection or abnormal reflection here. So basically using this kind of nanostructure, you can control the light in a different way. For example, you can control all the property of light, let's say the phase, the amplitude, reflection, and so on, using this kind of nanostructure here. But to give you a little bit more the physics out of this, you can imagine you have a metallic bar here. They are in a nanometer scale. And now you're putting a metallic bar on top of dielectric and metals. Now, because you have two parallel magnetic plates, when your light shines on top, you actually will form a magnetic resonance here. As a result, if you look at the reflectant, you see a magnetic resonance dip here. At the same time, if you look at the optical phase, you see the phase will change for 2 pi across this resonance. So what I mean is that basically one simple metallic bar, you can change the optical phase and amplitude. And this is some nanostructure you can use to changing the light. But what you can further do is actually you can changing the shape or the length of this matter structure gradually. Let's say in one axis, you're increasing the length. As a result, you're changing the phase across this axis here. As a result, you have artificial phase fronts. As a result, when your light coming in, you have a anomalous reflection. Instead of reflecting on a normal direction, we reflect in a different directions. And this is exactly what the matter surface do, is using the nanostructure to shaping the light locally, changing the phase of the light, and then you can changing any property you want using this kind of nanostructure here. So this is a really exciting and impressive nano-optical study, but to show you how impressive is that, here I'm showing you an image here, actually from the Capasso group as well, but we are doing similar things as well. So in the right-hand side, you can see with a normal objective lens you see in a microscope, or like my glasses, they're typically like really fake, like a couple of centimeter, millimeter scale. But on the left-hand side, you can see this so-called matter surface lenses. We're talking about 10,000 times thinner. So you can see basically really impressive. We have similar lens like on the right-hand side, but now we're scaling down 10,000 times thinner. And if you try to zoom in, let's say million times, you find that all the nanostructure here, basically using all this nanostructure, you can shaping the light and making a lens in a really small dimension. And this is actually so-called as matter surface here. So you can see that means you can reduce the size of the optics significantly using this kind of nanostructure, but not only for lenses, any optical component, let's say from mirror, beam splitter, polarizer, etc., you can imagine you can have a matter surface version. So that's why this is really exciting, because again, you can scale down all the optics in a really small dimensions, and you have new functionality. At the same time, the physics could be different here as well. So that's why this has been a really exciting field for optics in the last couple of years. And a lot of really fascinating property have been discovered. For example, you can control the polarization, let's say making voltage generations, making ultra thin lenses, as I mentioned to you, controlling polarization, say, or even you can have many different devices, let's say matter surface hologram and so on, using this kind of ultra thin optics. Again, a lot of fascinating applications, a lot of new development you can find using nano optics, and that's exactly why we are excited on this. But still, if you try to take a look on most of this report here on matter surface, they're passive structure. So that means once you fabricate a structure, you cannot change the property anymore. So let's say if we have a lenses, we have a fixed property, we cannot change it. But that's exactly what something we want to do in the research. We want to see if we can make something tunable. For example, if we can apply voltage to tuning the optical components, to tuning the optical functions. At the same time, we want to see if we can use some other interesting or extreme material to even enhancing some of these matter surface components, or at the same time, can we integrate this kind of nanophotonic metal surface to a different platform so that we can find different applications on that, for example, integrating the fiber for finding different optical applications. So this is some of the motivation of our research, and you can imagine against conventional lenses, they are quite thick, millimeter scale, centimeter scale. Now your metal surface is like 100 nanometers in dimension, but if you now can apply the voltage to tuning the focus or even controlling the light, speeding the light in different directions, there are a lot of potential applications on this. So there's some of the motivation we want to do in our research, in my research group. But anyway, this will be some of the topic I want to tell you in this talk here. I'll first tell you how we can make this kind of tunable metal surface. And then I will tell you some really interesting material called seal refractive index material, where you may not heard before. And then we'll tell you how we can integrate some of this nanophotonic concept to fiber optics application as well at the end. So let me first tell you about tunable metal surface. So to define what is tunable metal surface, you can imagine you have light coming in, you can reflect and transmit, and you have this kind of nanostructure here. And the idea, basically, we want to be able to control all the property, let's say, of reflection, transmission, or scattering by using this metal surface. And at the same time, active control, that means maybe applying the voltage, you can control the reflection and transmission in real time. And in a more like ambitious goal, that means you want to change basically all the property of light. Could be this spectral response, could be the spatial response, temporal response, or even the amplitude, phase, or polarization. So the ideal case here, basically, we want to control all the property of light using this kind of tunable metal surface here. So that means you can imagine we have one optics here. We can control all the function of optics by just maybe applying the voltage. That would be the long-term goal. But certainly it's not that easy to achieve, but this is something we're trying to achieve, is to able to have a full control of light using this kind of nanostructure active control. And there are many ways to control this kind of metal surface. We actually have a review paper published last year, try to summarize different mechanisms. I don't want to go for all the details, but basically you can do it electrically. For example, you can have some conducting material, 2D material, or liquid crystal, so that you can apply voltage to control the property, or you can have a kind of a thermal control using phase change material to control the material property to changing the metal surface, or physically changing, mechanically changing, or using nonlinear optics, high power laser, or even chemically, or using some fluid dynamic control. So there are many different ways to control this kind of nanophotonic structure. But in our opinion, the electrical control is still one of the best, because you can imagine like most of our devices, let's say electronic phone, etc., are basically powered by electronics. So that's why most of the application will be easier if you have an electrical control. That's why we're focusing more on the electrical control, particularly on the conducting oxide material here. So then the material we use is called transparent conducting oxide material. They are heavily doped semiconductor. They have high transmittance and visible and near infrared range. And this have been heavily used in, let's say, touchscreen or solar applications where you have high transmittance, at the same time electrical tunability here. So the good thing for this material is that you can actually have some tunable optical property. To show you the tunable optical property, I'm plotting here is a real part of permittivity. That means more or less like a refractive index of the material against a wavelength of frequency of light or wavelength of light, assuming one material, indium tin oxide material, is one of the transparent conducting oxide. And using a standard free electron Joule model, you have a capital N is a Kerr concentration, and omega P is a plasma frequency. You can see that by increasing the Kerr concentration, you can shift the dispersion to shorter wavelengths. And if you're particularly looking at optical frequency, let's say 1.5 micron in wavelengths, that means you can have positive permittivity, that means a dielectric property, or negative permittivity, that means a metallic property, depending on the Kerr concentration of the material. So you can see it's really good. That means just changing the Kerr concentration of the material, you can change the material property from dielectric to metallic, and the refractive index change is really large here. So in order to change the Kerr concentration, you have many different ways. For example, you can change it by fabrication conditions. For example, when you grow the material, you can change in the conditions so that you can have different doping of the material to change the Kerr concentration. But at the same time, you can also change the Kerr concentration by applying the voltage actively control. So that's definitely something we want to do, is to active control the material property. So then this basically we use the concept called a field effect dynamic control, which is something similar to what you learn in solid state physics, like an MOS transistor. You have a metal insulator and semiconductor here. Now, because you have an insulator here, if you apply the voltage, the electron cannot pass through because you have an insulator. As a result, you accumulate the electron, you're increasing the electron density. As a result, you're changing the refractive index of this layer when you're applying the voltage here. So to show you how this carrier density change, I'm showing you here as an electronic simulation of this ITO material. You can see applying the voltage, you can changing the carrier concentrations for maybe an order of magnitude. At the same time, if you look at the refractive index, they are actually changing quite significantly from positive to negative. So you can see it's really large change on the material property, optical property by applying voltage. But there one limitation here. If you look, take a look on so-called debye length, the accumulations length of this accumulation layer, we're talking about only 1 to 2 nanometer. So it's really thin layer, active layer here. That means if you want to take use of this active effect, you need to kind of combine to some of the optical structure. They have highly confined optical modes, something, for example, called a plasmonic mode or metasurface mode, where the light is propagating on the surface. So now if you kind of changing the material property on the surface, then you're changing the optical property significantly. So that's exactly how we take use of this tunable effect by combining some of the nanophotonics structure here. So then we integrate this to a metasurface structure. As I mentioned, a metallic bar can have a metasurface, but now integrating the active ITO material, applying the voltage, you expect to be able to change the property. So then if you take a look on the resonance, you see applying the voltage here, you're changing the resonance property. You're basically changing the phase and amplitude of light by applying voltage. And this is exactly what we want to do as a tunable metasurface, is controlling the phase and amplitude of light here. So then this is how we do that. And at the same time, you can imagine you can apply voltage, different voltage, different antenna, let's say maybe 3 of them with 1 voltage, another 3 of another voltage, so that you can making kind of active control on the phase. Let's say you can have a 0 pi phase change. That means you're making kind of phase grating here. So when you have a phase grating, when light coming in, then you will have a diffractions and you will able to diffract the light in a different dimension or direction here. So that means you can actively control, and to control the light, where do they diffract by applying the voltage here. So this is the concept here. To do that, you just need to applying the bias, maybe left and right and bottom in different voltage here, and try to zoom in the structure we fabricate. You can see we have metal layer, we have ITO here. You see some connection here, and the center is an antenna. If you zoom in further, you see antenna connections, and if you zoom in further, you see 3 of them connected to each other. And also zoom in, you see they are really nanoscale resonator here. So the good thing here is like you can apply the voltage on the structure, and then at the same time looking at optical property. That means you can do the change on the optical property in real time by applying the voltage here. So this is a structure, and then there's some of the results. You can see you have a resonance dip here, applying the voltage, you shift the resonance, you can change the reflectance for maybe 30% here. But more important is the optical phase. You can see we're able to change the optical phase for 1 pi phase shift, apply 2.5 volt here. So which is one of the really important demonstrations, showing you that you can change the optical phase by applying the voltage. And this is exactly what we want to do as a tunable metasurface, is controlling the phase by applying some external mediums, maybe a voltage here. So then we can actually also show that you can actively spin the light in different angle by gating it differently. So we're able to show that you can spin the light for 140 degrees by applying voltage to this nanostructure here. So the speed could be really high. We're talking about 10 gigahertz. At the same time, the power consumption is quite low because we are applying really tiny voltage here. So that's why it could be one really efficient way to make a tunable nanostructure. So using this mechanism, we also demonstrate other devices as well. For example, we make a color filter using metal insulator metal structure. We can have a color filter by applying voltage. You can tuning the color filter band at the same time, maybe turning off the color filter. At the same time, we also able to demonstrate a perfect absorber. Basically, you can have a structure with perfect absorption, but applying the voltage, you can tuning the perfect absorption wavelength. So we're able to modulate the absorption for more 100% here. So this is some of the demonstration that we can using this electrically control to control some of the nanophotonic structure quite efficiently, and some of the matter surface structure as well. So just try to remind you again, some of the long-term goal is that you can actively control so that you may be able to maybe tuning the focus or even spinning the light actively or changing any property by applying the voltage. This is something we can do as a tunable matter surface here. So there are many different applications you can keep in mind. For example, a CMOS imaging systems. For example, in our smartphone, there are a lot of optical systems, lenses, filter, or photosensitive element here. But at the moment, some of the thickness is still due to the bulky optics you are using. So you can imagine if we can make it ultra thin, so your smartphone at the end may be able to make much thinner using this kind of matter surface structure. At the same time, LiDAR applications like Tesla, Google car, etc., you may need to shooting the laser and collecting in the real times to see the environment. But at the moment, the LiDAR have a limitation on the resolution and speed. So some of this tunable matter surface could potentially helping on this area. And also AR, VR glasses now, really hot topic, like, Apple have a new glasses as well. So, but at the same time, you see there are a lot of optical components, let's say holograph, lenses, filter, etc. They are quite bulky. You can imagine using matter surface reducing some of this device application, not only for gambling, but even in US, they're actually using for training soldiers, etc. So there are potentially many different applications here. So in our review paper, actually, we kind of highlight what kind of application you can take use of this kind of ultra thin matter surface. For example, from communications to integrated fiber optics, LiDAR application, or even for space, this kind of light cell that we want to make it really thin, but traveling in space. So you can use some of the ultra thin matter surface for some of this application, AR, VR, for laser, or even for holograph, or even ultra fast technology. So there are a lot of potential applications that could use this kind of efficient active matter surface here. So in our research group, we have my student working on different areas. For example, some of the studies on a thermal emission control, making thermal photovoltaics, enhancing the efficiency of kind of photovoltaics, or using for advanced imaging for glasses, or even for fiber imaging, so biomedical application, endoscope, and so on. And also one quite interesting area we're also working on is, for example, integrating to laser as well, working with the group in France. We combine with some of the VCSEL laser. So basically, you can have matter surface on top of the laser. You can control the beam easily, let's say making a bezel beam or longer focusing length beams, or many different structure. You can have a structure like, so that you can use it maybe for spatial facial recognitions and so on. So you can making a lot of different new component from the laser directly, or at the same time, if we can make it tunable, then you can scanning in a real time as well. So there's some of the exciting application you can think of using this kind of nano active matter surface here. So let me move on to the second part. Let's see if any quick questions about the first part of my talk. I can quickly answer first. If
May I ask,
sure.
Are there any commercial product coming out of, I think, very generally?
Yeah. Yeah, it's a good question. So it's not completely commercial yet. So there are a lot of startup company actually kind of working on this area, making metal lens, etc. But some of the big companies, Sony, Apple, Samsung, etc., they're actually trying to integrate into their CMOS device, etc. So the big company working on this, but I don't think there are any commercial product coming out with matter surface so far. But a lot of startup company actually working on making device, because you can imagine it's a huge market, because any optics, let's say displays, glasses, you can imagine if we can reduce the size, there are a lot of market, and And even people trying to making a telescope lenses using ultra thin optics. You can imagine telescope, you have big lenses, but now if you can thin it down, that will be really advantage for, let's say, the space technology or any optics technology. So that's why a lot of huge potential, but it's still slowly going to the market soon. I would say in the next 5-10 years, a lot of things will be coming up with this kind of meta structure. So yeah, so if okay, so, sure. Mm-hmm. Mm-hmm. Mm-hmm.
It's really changing the optical properties of the aluminum, for example, oxide.
Mm-hmm. Mm-hmm. Yeah, that's right. The aluminum. Mm-hmm.
What is the typical wavelengths that we choose?
Yeah.
It's possible that you achieve kind of functions like
That's right. Yeah. Yeah, it's a good question. So typically the conducting oxide material, I think they are working better in the Lee infrared range. So that's why we're kind of focusing more on the Lee infrared range. To go to the visible range, a little bit hard to tune because you may need to have a higher K concentration of the material. So there's some other material that we can tune it in the visible, but for this conducting oxide material, probably we are focusing a little bit more on the Lee infrared range. Yeah. Like for example, 1.5 micron. So yeah, that's why it will be telecommunication wavelength. So, but we can also operate to, let's say, infrared range as well. So as long as longer wavelengths is actually not difficult, but going to visible range, they'll be more challenging.
1.5 micron.
Yeah, it's actually still quite okay. So the transmission is still quite okay in that range. Yeah. So it's not too bad, I would say. But certainly if we can find some high mobility TCO, then you can actually have a lower loss. For example, instead of ITO, we can have a cadmium oxide CDOs, and they have actually a lower loss. But for example, yeah, typically most of the device we're focusing on maybe Lee infrared range where we can tuning in this range. But some of the color filter, for example, let's say perfect absorber, we can even design maybe up to 700, 800 nanometer. So a little bit close to the visible range. But again, getting to the visible is more difficult to tune, but it's not impossible, I would say. So, but maybe the efficiency will be less. Yeah.
What is the typical operating voltage of this?
Yeah, we're talking about only less than 3 or 4 volts. Right? So really small amounts. Yeah, yeah. Because we actually use quite thin oxide, we're talking about 5 nanometer. So then you can use less voltage to kind of making larger change. So if you have thicker oxide, you need to apply high voltage, and particularly we actually want to make it smaller voltage operation. Yeah, sure, that's good. So let me move on to the second part. So tell you some really interesting material called seal refractive index material, where you may not heard before. So the seal refractive index material, and sometimes we call this an epsilon near seal material. Epsilon here means permittivity. That means the permittivity of the material is close to seal. Now, typically metal, the permittivity is below seal, negative. So that's why you see a shiny surface on the metals. Dielectric typically is a positive, refractive index 1.5 of glasses. And epsilon near seal means permittivity is close to seal. So this is really interesting with dreams, certain frequency or certain wavelength of light. If you have this permittivity close to seal, there are a lot of interesting physics and optics you can find this with dreams. You can imagine, just take a simple boundary conditions. If your epsilon close to seal, your electric field can enhance significantly if you're coming from one interface to another interface with ENC conditions. At the same time, if you kind of have a permittivity close to seal, that means your refractive index close to seal. What that means is that it's hard to imagine how the optical phase will look like with a refractive index close to zero. At the same time, the phase velocity of light could be really different as well. But that's why there are a lot of new physics and new understanding we can find this so-called epsilon near zero regimes. And particularly, if you take a look on the conducting oxide material, I just mentioned to you in the previous sessions. If you look at the dispersion, you see there are certain wavelength they're actually causing the seal. And this is exactly the ENC regime we're talking about. And you can see there maybe around near infrared range or close to visible range. And this is called the ENC regime here. And particularly in this regime here, there are a lot of really interesting physics that have been studied in the last couple of years, really fascinating optics. For example, people are able to making a Schwann-like absorptions, able to tunneling the electromagnetic wave or having a quantum property, enhancing magneto-optical effect, enhancing emission, or control emissions. And quite excitingly, they have some so-called non-linear optical effect, or you can use it for all optical switchings. So that's why it's a lot of really fascinating physics and application you can find in these regimes. And that's why I have been studying quite a lot on these physical phenomena here in our research group. But when talking about this ENC material, this group actually published a quite nice review paper and showing basically for different wavelengths or different spectrums of the electromagnetic spectrums, you can find different ENC material here. And the y-axis here is the loss of material. So basically, depending on wavelength you're looking at, you can find different ENC material. But particularly, we're more focusing on this kind of conducting oxide material because you can see they are lying in the near-infrared range where you can easily find a laser to shooting on this wavelength, at the same time finding different applications. At the same time, the losses is relatively low. The y-axis is losses. That's why we have been taking a lot of advantage of this conducting oxide to study this ENC property here. So then to tell you a little bit more what's the optics you can find on this ENC material, we're able to excite so-called ENC mode. So basically you can have a thin film here coupled with a prism with certain angle. And once you're able to excite this ENC mode, what you find is that all the light will confine on this ENC layer. So basically all the light will be highly confined on this layer. And what that means is that you can also imagine you can have really strong light absorption, basically perfect absorptions. And depending on the carrier concentration, you can even tuning this perfect absorption band to different wavelength as well. So again, one key phenomenon is like all the electric field or all the light will confine on this ENC layer if you excite this ENC mode here. And just to give you some remark here, the condition is really ultra thin when you talk about, let's say we talk about wavelength divided by 50, wavelength divided by 100 and so on. So that means if you have a, let's say we are looking at visible range, the device dimension or the thin film dimension will be talking about maybe 10, 20 nanometer, really thin structure. But at the same time, you need a certain combination of angle and thickness in order to excite this mode efficiently. So that's why we really need to have a good controls of the material in terms of the thickness and ENC wavelength when we study this kind of CO refractive index optics here. So that's why we have been using a technique called atomic layer deposition technique to making this material. And this ALD technique is a good thing is that you can do it layer by layer and we're going in an atomic layer thickness. At the same time, in each layer, you can control the material property. That means you can have a good control on the material. For example, we make an ACL material depending on zinc oxide aluminum ratio. We can precisely control this ENC wavelength quite precisely. And we're particularly looking on around 1.55 telecommunication wavelength here. Just to remind you again, this technique allows you to have a precise control on the thickness and ENC wavelength, which is something important for this kind of CO index study here. So, but other than that, we can also have a good surface quality. At the same time, it's a conformal deposition. That means you can also coating the side wall of, let's say, a metal surface, for example. So that's why we have been using this technique quite a lot to making this kind of ENC material. Then once you have the material, we can have a simple setup here. We have sample here. We have a super continuum laser, that means a Bob band laser, coupled to the sample, and you can collect with different angle with a spectrometer here. So this is one of the measurement result. You can see we have a strong reflectance dip for this 15 nanometer thick ITO. And this dip is correspond to ENC mode excitations. If you take a look on the amplitude here, we're talking about around 20 dB. That means more than 99% absorption. So you can see it's really impressive. Only 15 nanometer of the material can basically absorb around 100% of light here in a really thin film here. So by exciting this ENC mode. And as I mentioned, this mode excitation really depending on thickness. If you try to changing a thickness, you can see this excitations gradually reduce and also the ENC wavelength shifting as well. So that's why the ALD allows you to really precisely control the thickness and allow you to excite this mode more efficiently to study this ENC optics here. So then with this, we are able to demonstrate a perfect absorber using this ENC material. We can also make a broadband perfect absorber. Let's say instead of one layer, we have multi-layer with basically different K concentration of the material. That means you have different ENC wavelength here. And now we can get a collective effect. So you can have a broadband excitation and broadband perfect absorption here. So, and then at the same time, as I mentioned, we can use a similar effect to make it tunable, tuning the absorption band to different wavelength by electrical voltage here. So when talking about this broadband absorber, so here is only 3-layer structure, but you can imagine you can have many different layers here. Let's say 10 layer, 20 layer to get a broadband effect. And now you can imagine how can we actually optimizing this structure to get a really ultra broadband perfect absorber if you have many layers. It's turned out it's really complicated. So for example, you have a lot of degree of freedom. For example, you can have different thickness, you can have different material, different order. At the same time, you can have coupling between different layers. And at the same time, when you have many layers, you're making it really complex. And my student actually told me it's like billion years to compute if you have a really complicated structure. It seems like the student doesn't want to do the work and tell you it's take forever to work and you think need to do the work. But this actually is not true. It's a really, really complicated structure when you have a lot of layers when you don't want to do the optimization. It turns out we find we can use the neural network to help us to design. My really nice student, really interested on neural network, able to use the neural network to design and make a really ultra broadband perfect absorber. We're talking about bandwidth of 500 nanometer. More or less like perfect absorptions in a thickness of only 48 nanometer here for 10-layer structure. So you can see you can really design really well using a neural network to get a broadband structure here. Experimentally, we're able to demonstrate, let's say 3-layer structure using a neural network, we get a really broadband absorber, more than 500 nanometer bandwidth. And if you don't use a neural network, basically it's really hard to decide to get an ultra broadband absorber. So that's why we really think that we can combine some of the machine learning to nanophotonics and design some of this nanostructure at the same time, this kind of ENC material as well. So far I told you it's more or less like linear property, linear optical property of this material. But as I mentioned to you, a non-linear property also quite exciting property. Using, for example, a high power laser, looking on the material property. And there are a lot of exciting demonstrations. For example, people are able to show strong curl nonlinearity, creating high harmonic generations, or even using for optical switching and so on. And that's why I have been looking on this quite significantly. The key idea here, again, is if you can enhancing the nonlinearity in a really thin film, then you can make a lot of optical device in a really small dimension here. So there's some of the motivation here. So that's why we have been looking on nonlinear optical property. I try to show a really simple schematic here. Basically, you have an ultra fast laser, a short pulse, and shine on the material, and then you have detector and aperture here. And what we do basically scanning on the C directions. And because when you scan a C direction, you have different intensity, different focus. As a result, your intensity induced refractive index change will be different. As a result, your spot size will be different. As a result, when you scan a C direction, you can retrieve what kind of nonlinear property of this material. So just to give you some number here, may not be too familiar for you guys, but this is so-called nonlinear reflections and nonlinear absorptions, N2 and beta 2 value for this 76 nanometer ACO material. And just to keep in mind, this is like 5 order of magnitude normal, higher than normal glasses. Just keep in mind, let's say if you using a normal glasses, I mean a 1 centimeter, you're using a certain laser pulse, you want to induce certain phase change, and we only need to use maybe 100 nanometer of this ENC material in order to get the same phase shift using the same laser pulse. That means you can reducing the size of the material, or you can enhancing the nonlinearity of the material quite significant using this ENC material here. So then with this, we're actually studying different property, let's say angle dependency, because we know this mode is exciting depending on the angle and wavelengths. You have different excitation property. So that's why we look on the angle dependency. At the same time, we look at the thickness dependency, because the optical field confinement is basically inverse proportional to thickness square. So we want to see if we can reduce the thickness and enhancing the nonlinearity in this way. So that's why we have been fabricating different material, different thickness here, and looking on a nonlinear coefficient for different angle. You see in certain angle, you have a higher nonlinearity. That means because we excite the mode more efficiently. At the same time, the thinner the thin films, actually you have a stronger enhancement. So we really see a strong dependency on angle and thickness dependency as well. And just keep in mind, we also look at the ultra fast dynamics. I try to skip the details, but basically using a pump and pop laser pulse, and you have a delay line here. You can look at the ultra fast dynamic, and this is typically the result. You can see the relaxation time is quite fast. We're talking about 100 femtoseconds. That means you can use it as a really highly nonlinear material with a fast response time. At the same time, they have a quite high power dependency. So I try to skip the details, but we're able to control the nonlinearity of this material. At the same time, we find some interesting physics on this kind of ultra fast dynamic. But the key thing is, again, we can enhancing the nonlinearity using this epsilon near zero regime here. So certainly it's a good material, high nonlinearity, but we can combine with different application. We want to see if we can take use of this nonlinearity. So for example, we're trying to combine with a metal surface so that we can potentially coating to the metal surface of this ENC material at the same time applying the voltage to actively control that. And then we're able to making a control on the harmonic generations or even electrically control on all the optical property nonlinearity. So that you can use it for image encoding, imaging, or even optical switch and so on. Also, we find quite excitingly is you can integrate into the nano circuit as well. So previously we're using this TCO material, you can apply the voltage to modulate the signal of the nanophotonic structure. But now you can using a nonlinearity using, let's say, ultra fast pulse to modulate the signal. So you can imagine you can have a more complicated structure. Like coupler, you have a cos and bar, and you have an input here. Depending on the laser power, you're able to switching between the bar and cos, or you can even make a resonator structure, increasing the power, you can switching the different port here in a really small dimension. So this is something we think really excitingly using this nonlinearity here. So I was trying to skip a little bit of the details and maybe try to move to the last part of my talk because I'm running a little bit late on my time. So I told you about the nanophotonic structure, new material. And in the last part, I want to change the gear a little bit to tell you how we can integrate some of this to completely different platform, the fiber optic platform here. So I think some of you are really familiar with fiber optics. So basically, it's one of the best example to guiding light, most efficient way to guiding light using two pieces of glasses. But totally internal reflection on the glasses, high reflective index, you can transmit the light for really long distance with really low losses. And that's why you have a really fast internet nowadays using this kind of fiber optics technology. In my opinion, this is one of the most important innovation nowadays because like without internet, I think everyone cannot survive now. So the student cannot looking on YouTube, Facebook, etc. At the same time, faculty cannot check email, etc. And also maybe looking on YouTube as well. So everything will change without the internet nowadays. And that's exactly why the father of the fiber optics, Charlie Clouse, one of my favorite scientists, he has been working in Hong Kong for some time as well, got a Nobel Prize more than 10 years ago on his contribution using the simple physics to combine with the optical communication, making huge impact to the technology and also on the human life as well. So definitely optical communication is really important technology nowadays using fiber optics. But other than communication, there are many applications as well. For example, using for imaging inside your body like endoscope, like optical sensing. I think President Wei is one of the pioneers using a fiber sensor to tracking, let's say, the crack on the metro wheel and so on, or train wheel and so on. And even fiber laser, like creating different kind of new laser using fiber optics. So these have been really important technology. Many of them have been really mature and have been studied for a long time, 20, 30 years. But if you try to take a closer look on fiber optics, they still have some fundamental limit here. So the limitation, basically, we are limited by the glass we use. Because we're using glass, you have a material limitation. At the same time, we have a limitation on geometry. For example, if you want to make a single mode guiding, you need a certain geometry guiding light. And also, once you fabricate the fiber from a fiber drawing tower, all the property of the fiber optics have been fixed. For example, let's say empty phase or mole profile and so on. So you cannot change the optical property from fiber anymore. So you may be able to find some optical component change the property from the fiber. Let's say from 4-lab, you can find collimator, lenses, isolated, modulator, and so on. But you can see they're actually really bulky. They're not that efficient at the same time. So they're quite expensive as well. So that's why in my research lab, we are actually interested on the concept to combine some of the nanophotonics concept, meta-surface, new material to fiber optics, so that we can making a new functionality on this kind of fiber. For example, you can imagine you can make an ultra thin lens to focus light directly from the fiber. At the same time, like we want to extend the functionality, reducing the size of the fiber component or using for different optical excitation platform here. And for a longer term goal, we want to even make it tunable, as I mentioned in the first part as well. So you can imagine you can meta surface and actively control on a fiber, then you can change all the property on a fiber format here. So that's why in my lab have been integrating or fabricating different nano structure, let's say meta surface, nano wire, even nano circuit on fiber, combined to fiber optics to making a new functionality. For those of you not familiar with fiber optics is like a dimension of human hair, really tiny, and we are actually making some structure on the core of the fiber, so that we're really making some nanostructure, metastructure to integrate to a micron size structure to changing optical property of light here. So the word here means matter, you may know, means beyond in Greece. That's why we call this a meta surface, is a surface beyond normal surface. So that we have new functionality of the surface. That's why we call this a meta surface. And now if you try to search a meta fiber in Google, what you find actually completely different. You see a fiber wafer here. It's not something we prefer, but what we want to say is like we have a new functionality of the fiber by integrating some of the meta structure on the fiber to extending the fiber functionality and so on. So that's why we have been making different components. Just show you maybe one example, two examples. For example, we can making an ultra thin lens called a meta lens on a fiber to focus the light. To make a lenses like my glasses, you know, you need a certain kind of optical phase path. For example, I have a really heavy short sight. That's why my lens is really thick. So you need a thick curvature to focus the light in this way. So then that means you need a certain kind of phase profile if you want to make a lenses to create a certain phase profile. But in a meta surface point of view, basically they are just a flat surface. What we can do is actually using this kind of so-called geometric phase of this unit element here. Basically, just rotating this nanostructure with different angle, you can actually retrieve different phase here, but preserving similar with efficiency here. So that means just rotating the structure, you can produce certain phase of the light. And basically then you just, if you need this kind of phase profile, you just rotate with different rotational geometry to make your lenses. If you have different lenses, let's say different NA of lenses, then you just need to change the rotational geometry to different rotational geometry in this way here. So then to make it on fiber, then we coat the material on the surface and using a nano fabrication technique, focus ion beam to milling the structure. And just to take a look on this is a dimension of my hair, and this is a fiber optics, and we're making some structure on the center of the fiber. If you zoom in 1,000 times, you see a nano structure we make. So you see a tiny nano structure gradually rotating from the inside to outside so that you can get a certain phase profile. And once you make it, then you can make a focusing lens on the fiber here. So we skip the details, but this is a setup. We make the characterization. We have laser, we have a fiber with the meta surface on the end, and we have camera here. We just scan on the C direction on the camera. When you're in certain position here, you find a high intensity, and this is exactly the focal length of the lenses here. So then you can see like for different wavelengths, and you can have a focal length around 30 micron. They're quite consistent. And then if you make another lenses, you can have 40 micron focal lengths compared with simulations, and you can see we have a really good agreement on the focal lengths and also on the spot side of the focus as well. So over different wavelengths, you have a quite constant focal lengths, and just tell you a little bit about the efficiency. It's quite decent efficiency, around 15%. but we can actually make it even higher using other material. For example, instead of using metals, you can use a silicon. We're able to reaching around 90% efficiency here. So I'm running a little bit late, so let me tell you, other than lenses, we can also making a color filter. For example, we can make it on different type of fiber. Now you can have this kind of unit element, X and Y, have different dimension here. So now again, we fabricate, let's say, a symmetric structure, asymmetric structure on the fiber against on different type of fiber, or even single mode fiber here. You can see covering the core with a symmetric structure. So this is a measurement result. You can see a symmetric structure, X and Y polarization, say you have a same transmission band, but now you're changing the to a symmetric structure, depending on X and Y polarization, you have a different transmission band here. So that means you can really decide, depending on your lens structure, your optical function here, and compare with simulation, we have a really fair agreement. So I show you different demonstration integrating on fiber, this kind of lens structure. At the end, we want to make it tunable as well. Applying voltage, you can make it tunable. There are a lot of potential application here, can emergence like, for example, endoscope. So people using fiber optics to imaging inside the body. But if you take a look on the endoscope, they are really complicated. There are a lot of optical components, let's say beam splitter, lenses, scanning element, they are really bulky. So you can imagine using some of this component to reduce the size of a fiber endoscope. At the same time, for surgery as well, so a lot of fiber surgery using laser to killing tissue and cancer, but at the moment there are no efficient way to control it. So using metal surface or tunable element, you can making active control on the light or polarization and so on, or even optogenetic, people using fiber optics, using light to excite the neuron, controlling the neuron activity. But now again, at the moment, there are no efficient way to controlling the light properties. So using this kind of lens structure, you can control quite precisely as well. So we really think that there are a lot of potential application in terms of medical application, endoscope surgery, imaging, as imaging inside the brain or inside the body, or even using for communication, multiplexing, mode conversion, or even for laser device, fiber laser device application. So this is something we find quite exciting, is integrating metal surface on fiber for different application here. With this, let me quickly conclude. I told you about tunable metal surface, zero index material, and integrating some of this nanophotonic to fiber optic applications. I want to acknowledge the people in my group. Without their hard work, I cannot tell you all the result here. At the same time, the funding agency support as well, and also acknowledge the collaborator from the US, let's say in Texas, or National Lab, or even Harry Edwater at Caltech, and different people in Europe, and also different people in Asia, for example, Dimping Chai, and also a couple of folks in Taiwan and China, and also the funding agency support as well. With this, really thank you for your attention, and happy to answer any question as well.